Hey guys, welcome back. Hey everyone, good morning. Let's uh let's get started. So going with the recap of the second last session, this is supposed to be your this will be most probably your second last lecture because we only have one more class left. So either we'll complete everything by tomorrow. If needed, we might extend to Friday, but most probably we should be able to complete by tomorrow. Okay. So the last session will be focused on deep learning, where we'll discuss some of the architecture, not the exact architecture, but we'll be discussing about the algorithms. And this lecture will keep it focused for chatbot because that's one thing which is left. And we'll also discuss about hidden Markov models, which was left yesterday, right? So once we discuss hidden Markov models and the chat, only thing that will be remaining is deep learning. Uh, and a lot in deep learning, we'll see like some of the very important topics like BERT of how people have dealt with BERT over the years. Okay, so let me share my screen. Let me just show you. All right, let's begin. So a quick summary of whatever we have seen in the last lecture. So we had discussed about your two things. One, majorly we focused on pure style. Second, we discussed about name entity recognition, NER, right? So we discussed NER is a special case of pure stacking where we identify the main entities. Now we had also discussed the different models which can help us do. Pure stacking is performed by hidden Markov models. NER can be performed by models like LD, right? And we had discussed about LD as well. Now, coming specific to the hidden Markov model, let me just write it over here. So, hidden Markov models, short formed as HM, are those models which basically help you deal with the probabilistic states. Okay. So, what happens is these are probabilistic models. That means they will generate some probability, right? And these models decide next state based on the current state. Okay. So probabilistic models, but they have the ability to decide the next state based on current state. So for example, What happens is in NLP, let's say you want to predict, we want to predict the next word based on the current word. Okay. For example, when you try to send a WhatsApp message, right? We have seen in the WhatsApp message when you type like how are, automatically WhatsApp will start suggesting you the next word as you, right? So how does WhatsApp identify that this is the word that has to be shared? Okay. So over here, you're trying to predict the next word based on the latest word, on the current word. Okay, what is the current word? And that's the main logic of hidden Markov model. Okay, so what it's going to find out is it finds out something called as a transition probability. Transition. What does transition probabilities imply? The name is coming from this transition only, as you are going from transition from current word to the next word. That is referred as transition. Okay, and the probability of going from that word to the other word is called as transition probability. Okay, so in this case, you are going to model this as a Markov model. Okay, so what we are going to do is Markov model says if you move from word one to word two, if you move from one word to another word, okay, when you're moving from this particular category, like one word to another word, you need to find out the probability of that happening. Like, what is the probability of moving from word one to word two? Okay, find out the transition probability for that. Okay, so what is the probability of going to word one from? Sorry, what is the probability of going to word two from word one? So over here, you will find out how. Yeah.
It should be probability of word 2 given word 1, right?
Probability of word two given word one. Just a second. Yes, I think this should be there. I believe this makes more sense. The only reason why I'm choosing this is because since it's a conditional probability, you're saying that given you are at word two, you need to go to word one, right? So that's the only reason. Let's
No,
say,
no, no. I'm
sorry.
saying like the probability of word 2 given that the word 1 we already know.
Yeah, sorry. I meant that only. I just
Yeah.
wanted to reverse this. So given that you are at word one, what is the probability that you can go to word two? So let's say if you are at a particular word, what is the probability that you can move to the next one, right? So word two, given you are at word one. Good. Um, just a moment. Okay. So actually, this, in my opinion, can be defined in both ways also. Okay, it can be defined through this as well. The reason over here, we are saying that what is the probability of next, say, what is the probability of, right over here, probability of next state is equals to word 2 given the current state is equal to word 1. Okay. But if I reverse this, if I write what is the probability of current state is equals to W1 given your next state. Okay. Given your next state is equal to W2. So let's say if you're going from one place to another place, given that you need to reach this particular place, given that you have to reach word 2, what is the probability if you start from, if what is the probability that if you had started from word 1, let's say there are multiple words, if you had started from word 1, what is the probability that you'll reach the word 2? Okay. So this can be framed in both the ways. We can, so according to the calculation, since we'll be taking a multiplication, ideally if you either go with first one or go with the second one, follow it consistently, like follow for all the words. Okay, at the end you'll get the same results only because we'll be multiplying this, right? So when we will multiplying, a lot of these things will get opened up. So probability of, because over here what we'll be doing is you have probability of A given B, which is nothing but probability of B given A into probability of A divided by probability of B. Okay. Now you'll be multiplying this continuously. Okay, I'll talk about what we are going to multiply. But when you have multiple words in a sentence, right? For example, IPL is going on, right? What will we find out is now after following the sentence, what is the probability of going from one word to the other, right? So let's say if I have reached on, from here, uh, if I write like on, what are the different options? Let's say the first option is on, let's say Hotstar. Right? Second option is, let's say, uh, since. Okay, maybe since last 10-15 years, something like that will write. But the next word should be like, one of the option can be since. Okay, IPL is going on, and there could be other options as well. Over here, you are finding out which word should come next, right? One thing that we'll focus is finding out the probability that, hey, what is the probability of the transition, right? Going from on to the hot start. Now, if you define that the probability is either defined by this logic or this logic, whatever you define, maintain that for rest of the words as well. Like once, okay, once you find out this probability, okay, A given B or B given A, from let's say on to Hotstar, you'll find out the same probability for on to since. Okay. and let's say finally you see the probability of Hotstar is the highest, will once we decide like, okay, we write Hotstar, and after that Hotstar, you need to predict what will be the next word. I'll again find out the same probability which I found out earlier. Okay. And based on that, I'll decide what should come after Hotstar, right? So over here, in our case, we are defining the transition probability using this logic. The only reason why we are defining a logic using this particular logic is because online articles may you will find the next state to be written first. Only reason being where next state to be written like over here in the first part as in the given statement. Like only reason being you are following you are going to follow a map because we have not seen the map, but the name is Hidden Markov Model, and this is coming from the logic of Markov chain. Okay, the logic is based on Markov chain. So Markov chain looks something like this: like you have a state and you go from one state to another. Okay, so let's say this is state one, this is state two. So in our case, we don't call it state. State is something coming from theory of computation, but over here we'll call it as words. So you're going from one word to another word. Okay. So based on that, we are defining our outputs. But even if you change it, when you get the final answer, the probability of a sentence will not change. So what we have to do is we have to find out transition probabilities of every single combination, right? Like not every single combination, as the consecutive combinations, right? So once you have written, let's say IPL is going on, after on, what is the probability of on with Hotstar? What is the probability of on with Sense, right? Once you decide like the probability of on with Hotstar is the highest, you will check, okay, now Hotstar is the next word, but what will come after that, right? So after Hotstar, what is the next probability? Okay, Hotstar with something. Okay, same logic will apply in Google search as well. When you search something, it shows you a complete sentence when you type like couple of words. How does that happen? Same logic, right? So over there, they will search what word you have written, and based on that, what is the best next word that we can write out. Okay, so over here, I'll just go a little more specific into the algorithm. You find out this probability of current state given the next state, and you find out for all the consecutive words which are yet to be typed. Once you have found out all the probabilities, what could be the possible words that could come up? So let's say now you have word IPL is going on Hotstar, right? Now let's say you started finding this probability right from the first word. Like you wrote IPL, and after that you found out all the probabilities. Like you found out the probability of is going on and Hotstar because the user only typed IPL, right? And based on that, you found out this particular probability. So you would have found out some probability of finding IPL given is, right? You would have found out the probability of is given going. Find out the probability of going given on. And one more probability that you would have found out over here is probability of on given it's Hotstar. Okay. So over here, you would have found out all these probabilities, right? So in the first one, where let's say you are saying your current state is set as IPL, what is the probability your next state is going to be set with is, right? So given your next state is going to be is, what is the current probability that your current, what is the probability that your current state will be IPL, right? Because you had typed one word, which was IPL, right? Now, if you're finding out all these probabilities, what are you going to do is, let's say this property is A, this is B, this is C, and this is D. I have found out all the pair consecutive probabilities. All of them are transition probabilities, which tells what is the probability of going from one word to the other. Now, in hidden Markov model, to find the probability of a sentence occurring, like whether if I type an IPL, whether the sentence should be IPL is going on Hotstar, or let's say if the sentence should be, okay, I've typed IPL, or the sentence should be IPL match schedule. Okay, between the two sentence, which sentence should be recommended, right? Over here, again, we'll find out this. Over here, we found out the probability of A, B, C, and D, right? This were the four probabilities that we needed, A, B, C, D. Based on that, we'll multiply A, B, C, D, A, B, C, D to generate your final transition probability. Okay, so that product of all the transition probability will tell you what is the probability of that sentence. So this sentence 1 and sentence 2, you find out what is the probability based on multiplying consecutive words. You will get the probability of sentence 1. Same thing you do for here as well. You find out the transition probability from here to here to here, and multiply both the probabilities A and B, right? So you multiply A and B, you get the final product. That will be the probability of your sentence 2. Okay. So hidden Markov model says you build a Markov chain. Markov chain is nothing but you find out the transition probability of moving from one word to the other word. And finally, you combine all the probabilities by taking a multiplication, taking a product to find out the probability of a sentence, okay, or the total sentence. So here we are saying probability of sentence 1 is, let's say, 0.7. Here, the probability of sentence is, let's say, 0.9. Since probability, it will lie between 0.0 to 1 only. Okay. So in this case, since probability of sentence 2 is more higher, we'll say that sentence 2 should be recommended over sentence 1. Right. So I'll probably recommend this sentence to IPL match schedule over IPL is going hot on Hotstar. Okay. If the person types IPL. Okay. Okay. Going a little more specific in the details. Okay. So this is where we define that you go from one state, like you are going from IPL, you are going to the word is, you are going to the word going, going to the word on, and so on, right? And then you have another possibility that IPL, another word is, let's say, match, another word is schedule, right? And similarly, you can imagine there could be other possibilities as well, right? So all this, like as you're moving from one state to the other, this process where you find out the transition probabilities is called as a Markov chain. Okay. All this are Markov chain where you're finding out which chain has the highest probability of happening, chain 1 or chain 2, right? And finally, you generate the transition product of transition probabilities. Okay, so here you started with the current state. Okay, and finally you'll go to the final state wherever you want to terminate. Over here, Markov chain is a transitive pattern, like you are moving from one state to the other. With each state, you are storing some probability like 0.7, 0.8. This probability is nothing but the probability of, or actually let me write it over here, 0.8. This is the probability of moving from is to going. Okay. So what Markov chain said is you find out all these probabilities, you take the total probability of the chain, you will understand which chain has more chance of occurring. And that chain is the sentence, right? If chain 1 has more chance of occurring, like this particular direction, you'll say the sentence is the one which is better. Now going to the hidden part. So we saw Markov, but what is hidden in it, right? That's the final part. Now in Markov, we find out the hidden part, which is the hidden state. So Markov model has something called, sorry, hidden Markov model has something called as a hidden state in between. Okay. What is this hidden state? As the name says, it's going to be hidden. And what does it do? It basically introduces, it's a like a it's not something which you can observe. Okay, it's something which is getting computed internally. Okay, but it is one property through which you can through which the models HMM can be used for POS tagging. Okay, so whatever words that you had, right, for example IPL is going on, we are finding the transition probabilities from one word to the other. Okay, which is observed. Why observed? Because you can see the state for it, right? You can see the state that IPL say you're going to is, right? All the states are visible. So just give me a moment, guys. Just a second. Okay, so over here we are finding out the probabilities of IPL say is, then is to going, and so on. Right? You're writing all the words, the possible words, and finding out what are the transition probability. Now the thing is, hidden Markov model says you can have a additional hidden state which will help you with POS tagging. Okay, so it's going to tell you that hey, the words are attached to which POS tag. Okay, what is the POS tag of every single word? Okay, this state can't be observed. Okay, we can't see this. So this will happen internally because it's a hidden state. Over here, what will happen is you will see for every single word what is their POS tag. So for IPL, what would have been its POS tag? For is, what would have been its POS tag? Right? And so on for every single word. POS tag will simply say like IPL is probably name of a not an organization, but let's say name of a tournament. Right? So it tells you that it's something to do with tournament. Okay. Oh, by the way, we are using not name entity recognition. We'll talk about NER later. So if you know about NER as we discussed yesterday, right, this would return tournament. But since we are only right now talking about POS tag, this would only return whether what is the part of the speech, whether it's a noun, whether it's a verb, whether it's an adjective, adverb, and so on, right? Similarly, it will return same thing for all the words internally. So you'll get to see what is the POS tag. I mean, as the model will know what is the POS tag. Now, over here, we are introducing one more type of probability considering the hidden state, which is called as emission probability. This is occurs only in HMM. So Markov model only has transition probability. In Hidden Markov model, we are introducing a new probability called as emission probability. Okay, emission probability is based on your hidden state. What does it say? It says basically that what is the probability of an observation given a particular hidden state. Okay, so given, so let me write, okay, which in our example converts to what is the of a word probability of a word given its hidden state. So given its pure stack. Okay. So over here, what we are finding out is probability of a word given its pure stack. What is the probability that, hey, if you know the pure stack for a particular this thing, like for a particular word, for example, let's say you are having, okay, let me write it over here. You have a particular pure stack. Let's say over here, this is noun. Let's say this is over here is adverb. Okay. This is, let's say, a verb, and let's say this is a preposition. Okay, these are the part of speech which are there. Now, what it says is, given that you know for IPL, the part of speech is noun, because IPL is something which you're starting with, right? So, given that you know its pure stack, what is the probability of the next word, right? Probability of the word which is going to occur after that. Okay. So, based on this information that noun is the first word, right? Which word can probably occur later? Because now there are some rules through which we write English sentence, right? For example, if you write IPL is going on, after a noun, a verb can follow. So not a verb, but a adverb or can follow, right? Is can follow over here. Okay. But after a noun, can a verb directly follow? This can't happen, right? I'm just taking like a very simple example, but you can understand that there are some rules according to which how noun, adverb, word should be placed, right? Sometimes we can't have noun just after the verb, okay? Or maybe let's say if you already have a combination of, let's say, adjective verb, maybe a noun can't appear after that, okay, unless and until you have something in middle. So based on that, you are identifying, hey, if the word is noun, what is the chance of the next word to be, right? So now your probabilities are going to be based on the pure stack as well. Okay. So you will compute the emission probability. You will get to see that, hey, based on the emission probability, which words can occur along with the previous probability, which is your transition probability. Okay. So transition probability, say you will see probability of word 1, sorry, word 2, probability of word 1 to word 2. Emission probability, you will get to see what is the probability of POS tag of W1 to W2. Okay. The reason first one is advantageous because you get to see what are the multiple options, right? Like, do you need Hotstar? Do you need on? With the second one, what is the advantage? You are also getting to see the English framing, like English sentence, right? Because we know, according to English, there are some things which possibly can't occur, right? For example, maybe a verb has to come after a noun, something like that. Or maybe an adjective can't just come before a verb, right? So based on such rules, this emission probability will help you. It will help you in identifying that which part of speech should be together. Okay, and this is reversible. Okay, that means if you change A and B, or if you change B or A, right? Like this is A, this is B. If you change this, the final answer won't change, because at the end you'll be computing the total probabilities. Okay, you'll be taking a multiplication of all the probabilities to get the final probability. I'll talk about how do we compute the total probability. Yeah.
So this transition probability and emission probability, both the probabilities are considered, right? So for the sentence which is having the highest transition probability and emission probability, that one will be recommended. Is it so?
Yes. So emission probability you will find out for every
Yeah, it
single
is
word.
hidden.
Yeah, yeah. So final conclusion over here will be based on this thing, the first probability, transition probability of it. Like you'll find out the product of each transition probability, and based on that, you'll be comparing sentences.
So
But how?
internally, first emission probability will be working, and after that, transition probability will be calculated. Is it so?
Yes, like individually for every word, you'll be calculating both parallelly, transition and emission. But finally, to decide between, let's say, two sentences, once I know that, okay, sentence one is an option, sentence two is an option, to decide between them, will you make use of the first probability? Okay, this product seems to be higher for transition probability for S1. I'll go with S1. Emission ka use is only to make the sentence possible, like what is the
Okay.
option available.
Okay. Got it.
Okay. Hmm. So let's take an example. Over here, let's say one example is, let's say John runs fast. Okay, let's say this is one sentence. Now, what will happen with PO stack? Since the hidden state, based on the PO stack, it will identify this is a noun, this is a verb, okay, and this is a adverb. Right? So over here, your hidden state is noun, verb, and adverb. Your observations are what the person is typing. Let's say if the person has typed John, John will be your observation. You find out all the probabilities, right? All the conditional probabilities, the transition probabilities. Okay. So over here, I'll find out what is the different transition probability, like runs fast and John runs and all this, right? Once you find out all the transition probabilities, you'll also find out the emission probabilities, like what is the probability of run given it's a noun. Okay. You can interchange this as well, but ensure you follow one consistent pattern. Okay, so probability of runs given the last one was a noun. Okay, similarly, I can find out for multiple things. And now this will tell me which word is more likely to occur. Okay, so once we have found out the emission probabilities, once we have found out the transition probabilities, how do we finally conclude this? To conclude this, we are going to make use of one more thing, which is called as a Viterbi algorithm. Viterbi. Okay. So Viterbi algorithm, it's a dynamic programming approach. It's something which was made by software engineers. Okay. Dynamic programming is one of the toughest problems to solve in software engineering, right? People who come from computer science background would know about DP problems. These are this requires a huge amount of coding and logic. Okay, because they are not so straightforward problems. But anyways, we won't go into the specific of the Viterbi algorithm because we are not supposed to see this from software engineer angle. But I'll just give you a small intuition of what will happen. So what will happen is, once you find out the emission probabilities, and for every single word, you calculate the transition probabilities. Okay, the at the end, finally, you will decide which sentence is having the highest probability, right? That's how we are picking up the sentence. Okay. And once we decide that, like once you have state one, state two, state three, state four, let's say this is one option. Another option was this one, this one, this one, this one. Okay, let's say this is state sentence two. Once you find out, okay, the final probability of this one is higher, you will trace back, you will go over here, you'll fetch all the states, like you'll fetch all the words, and you will give that as the output, right? Whatever the words were there, you will say that this is the best sentence. Okay. Okay. Now that's the final end. But coming to the point where how do we utilize the Viterbi algorithm? So Viterbi algorithm may, since it's a dynamic approach means it has the capability to remember path, right? For example, if you are going from one page to the other, it will memorize from where did you start. Okay, this will come very handy when you have to code this. Okay, so it will remember that you move from this state to another state. You move from one hidden state to another hidden state. You move from one word, like from the current state to the next state. Okay, now this is very difficult to do in programming. Like in programming, it's very difficult to find out which combination should we follow, because imagine there will be 10,000 combinations, right? Like millions of combinations of sentences which can be there, right? And everyone will lead to multiple other options. It's not going to be like a straight line. Like this will have other options, this will have other options, right? Because after every word you can have multiple options, right? So this becomes a very complex problem. And if you are over here, okay, you need to understand from what all options you have begin, right? What were the previous options? You need to store that data somewhere. And that is where dynamic programming comes into the picture. It says that, hey, I will give you a optimal solution. Okay. Dynamic programming is the best possible solution that you can have for your graphical problems. Okay. People who know CS, they might have heard of something called as a Jigsaw algorithm, right? Your knapsack problems. All of them are complex problems, which are very difficult to solve. Even the problem of, let's say, the chess, right? In chess, you have a queen, right? I'm just giving you software engineering examples. So in chess, let's say you want to understand, let's say you're creating an AI based chess model and you want to understand like what possible combinations can occur. Like you have a queen over here. Where all I can play the queen, like what are the possible, like queen can go diagonally, it can go straight, it can go this way, right? There are these possibilities. But let's say if I'm planning my chess move, if I reach over here at this square, okay, then again I can go here, 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 I can go here. All these possible states needs to be stored somewhere, and that is where dynamic programming will come handy. It will help you in understanding what all set of combinations can occur, and it will give you an optimal way of storing this data. Okay, and the specific algorithm that we are using over here is Viterbi. We don't have to go into very specific of how dynamic programming works right now because it's not needed, but you should know that there is something called as a Viterbi algorithm which will help you in solving the dynamic problem given over here. Okay, what is the dynamic problem? The dynamic problem is to remember the states, to ensure that how do you understand you are able to handle so many complex states. Okay, so this will help you in coming up with the optimal answer. Okay, so let me just write over here Viterbi algorithm. will give you the optimal answer, because you can imagine to create a code, something like this, where millions of possibilities exist. It's a very difficult task. So if you don't use dynamic programming, you will see the time complexity, the time it takes to complete the process will be very high. Second, it's efficient because dynamic programming. Okay. Why is it efficient? Because based on the Viterbi algorithm, you will be computing even like you would have stored the previous output. And also, since you're combining Viterbi algorithm with your probabilities, what you have, the emission and the transition probabilities, you are only focusing on those sentences which are most likely, right? So I can actually define, let's say, a particular threshold. If the probability is greater than 0.7, then only consider that. Else, don't store those words. So I'm just cutting down on my chain, right? So it focuses only on the most likely words, which is more efficient. And finally, it gives you a clear path. It gives you clarity. So why clarity? Because it helps you in coming up with a clear path or clear path options that you can follow. Okay. So this is in a way very efficient for people who are trying to create big sentences. Okay. Okay. And finally, backtracking happens. Okay. Backtracking is again a very powerful concept coming from software engineering, which says that once you have reached the final state, like once you have reached from the current state to the final state, to figure out what were the words stored at each place, right? You will have to backtrack. Okay. You will have to backtrack starting from the final state using the pointers that were saved when the time you came on. So let's say you travels through this path. Okay. Let's call this node A, node B, node C, node D. This E, F, G. So now that you took ABCD path and you move from A to D, where D is your final state, it says that, hey, I want you to remember that you have taken a path of A, B, C, and D. Okay. And I also want you to understand that if, let's say, I have to go back to state B, that means if I have to go back to the word B, why B? Let's say a person deletes the word. Like if I wrote A, B, C, D, but I deleted D and C, I came back to B, right? So I don't have to compute. I shouldn't compute for B once again. I shouldn't compute the properties for B once again. I shouldn't create this chain A and B once again. That should not happen. If I am going back, if I'm going backer into any of the words, we ideally should have that because we have already computed the probabilities. And that's what backtracking implies. If you have to go from the final state to the previous state, you already have those values stored. And using those values, you can simply see if you were at B, what were the existing possibilities? Like if you were at B, C is another possibility. There could be another possibility, which could be, let's say, H. Right? And that is how backtracking happens over here. So in a way, Viterbi algorithm using backtracking is saving the information which it had stored while it was starting the traversal, and using that you can always remember what was the sequence of state, so that if you have to backtrack from the final state to a particular state, you can always know what was the other option. You don't have to compute it once again. Okay, so hidden Markov models are very efficient algorithms when it comes to predicting your next problem, predicting your next word. Okay. Markov because it follows the rule of Markov chain, hidden because the states are hidden. And finally, talking about its application, and we'll see a real demo of this. Okay. So where do we use hidden Markov models? Okay. Wherever you are, you have to predict the next word given you have typed in some word. Okay. For example, So for example, when we are talking about, let's say, speech recognition, okay, how can we train this? Like if you are training, let's say, Alexa, how does Alexa understand what speech it has to like say? That's based on the concept of phoneme. Like phoneme is nothing but the pronunciation of the word, right? Like the basic pronunciation of every word. So it understands, okay, what are the pronunciation of words, and you're storing the pronunciation in form of observations. Okay, you store the phoneme of, let's say, the word. Take any word, let's say hat. Okay, you will store what is the pronunciation for hat. Then you will store what are the pronunciation for different other words, like is ka pronunciation, had ka pronunciation, and so on. So here you're storing the pronunciation instead of storing the words, right? So you will go with exact phonemes of it. And based on the same logic, you will be able to, like Alexa will be able to train that, okay, now I need to speak this sentence because these are the phonemes which are having the highest probability, right? And that's how it will speak those words. Again, you can have many other advantage of this. You can use this in um, you can use this in even in weather forecasting. Okay, given your recent days, like day one, day two, day three, day four, and so on, given that respective weather has been so and so, like this was rainy, this was rainy, this was hot, right? What could be the weather over here, right? Will it be hot? Will it be rainy? Will it be humid? What it will be, right? And you can identify that based on a chain. Based on the chain, you can take a call for that. Even for many other applications like in bioinformatics, okay, in bioinformatics, you can use it to understand the gene history, the gene prediction. Okay, because every information is stored in form of DNA, right? DNA which will encode the genes. It has like the gene information present. So let's say you have gene one, you have gene two, right? Based on different DNAs that you are storing. Okay. And now for the history of a family, you can see that their DNA for, let's say, for the most senior person, you have gene one. Then for the next person, you have gene two. And this gene two is giving birth to, let's say, another gene three, okay, and gene 4, two children, gene 3 and gene 4, right? And let's say this is giving birth to three children, okay, something like here. So if I have to identify the ancestral history of this person, I can simply use backtracking, go back and find out the ancestor, right? I can store all this data in form of gene. How this will be useful? This will be useful in identifying that um, like where the gene is originating from, like what has been the ancestor history of a particular person. Okay. So this is again based in DNA form. Okay, so let me show you a working example of hidden Markov models. Okay. Let me show. Okay, let's see this. Okay, so let's read this article quickly. So over here, HM over here, it's trying to predict the weather. Okay, it's trying to predict the weather based on the type of clothes someone wears. So over here, the problem is different. What they are predicting is you are going to see what kind of uh, for every day, like for previous day, for present day, and for next day. The observation is on present day, the person wears this thing. On the next day, the person is wearing this cloth, and on the next day what is the person going to wear. Okay, that's what is hidden, right? You can see this is hidden. That's what you have to identify. So over here, the hidden state, instead of pos tag, they are making use of the weather information. Okay, they are storing the weather information as a hidden layer. Okay, so pos tag is for messaging, okay, where you need the information of words and all that. But in case of predicting for clothes, right, clothes won't be dependent on, like if you want to predict the clothes for tomorrow, obviously it won't be dependent on the words, right? It will be dependent on other factors which you are storing as a hidden layer over here. So instead of storing pure stack, you are storing whether the day information, whether that day weather was hot, mild or cold, right? So now let's say you know that, hey, previous day ke liye it's hot, present day ke liye it's mild, next day ke liye you have predicted cold. Based on that, like if the next day is going to be cold, what will be the suitable clothing that the person will wear. Okay, that's what we are saying. This is the observed thing, and this is what the hidden thing. Okay, and now you'll find out all the probabilities. You'll find out the transition probability, you'll find out the emission probability. This is the initial state from where you're starting. Okay, so priors is nothing but this is your this is what you'll compute for conditional probabilities, like what is the probability of hot, mild and cold. And then you find out the transition from one word to the other, from hot to hot, hot to mild, hot to cold. And emission similarly, like from pos tag to your particular word, right? This is your dynamic programming. This is, again, as I said, it's a complex problem. It's based on recursion because dynamic programming is highly complex. It uses the concept of recursion. We won't go into dynamic programming for now. Okay, notice over here, you're finding all the probabilities, okay, from given state to another state, like state A to state A, state A to state B, state B to state A, state B to state B. Okay, over here, like as you can see, different properties, same properties you'll find for emission as well. Like consider one of them is a pure tag and one of them, the state, is the observed word. So you're again finding the same thing. Like if the pure tag was red, what is the next probability? Same thing you are finding over here. If the pure tag was green, what is the next probability of the next state? Okay, you'll find out all the combinations of probability, and you'll simply, to get the final answer, you'll multiply all the probabilities which you have found over here, right? Whatever probabilities you have over here, you'll simply multiply to get the final answers. Okay, that will give you a final score which is 0.75 for a observation, for the observation that ABA green red is occurring together. Like, I mean, this is a different problem. This is not the same problem. Okay, this is talking about this example, like what color combinations should occur. Like this is a toy example. Okay, so if you read the algorithm, okay, what this says, generate the initial transition and emission probability distribution from the sample data. Okay, here it's talking about like plotting the histogram and getting the probability distribution. But even without that, you can simply find out all the possibilities. Generate what are the possible sequences, like things which we have not seen, which are unknown. You try to predict, like this is the possibility of sentence one, sentence two, sentence three, sentence four. Probably and apply a cutoff. That probability of transition should be the total probability, the multiplied probability should be greater than 0.75 for the sentence to be considered as an option. And finally, you score everyone, you decide which one is the highest total probability sentence. Okay, that will be your best sequence. Okay, that's what it's happening. Here in this code, it will generate all the unknown sequence. We don't have to go into details of this because now we have a library to do all these things. But this is for software engineers who probably want to write this from the scratch. Okay, but still, if you are interested, you can practice this out. You find out like what are the different possibilities based on the states that you are in. Find out the possible possibilities and score all the possibilities, right? Based on your hidden Markov models, based on your total transition properties. Right. So over here, this is the Viterbi algorithm which they are using. Right. So here you're seeing like not this one. If you're seeing over here, optimizing the efficiency of HMM computation using dynamic programming. Okay. As I said, dynamic programming will give you optimal results because you know, first of all, where to focus on, which are the ones which are more likely. First thing. Second thing, dynamic programming is very efficient whenever you are solving any graphical problem. Okay. Because compared to any other option, dynamic programming remembers the state. That's the best thing. Okay, these are like some additional things which we don't need. Cache recursion, performance improvements, all these things we don't look at it, like forward algorithms, backward algorithms, MBR scores. This is all from software engineering for optimization purposes. Right? So I would say like no one is going to ask you explain Viterbi algorithm or explain the concept of dynamic programming, at least not in the data scientist roles. Unless until you're applying for a role which requires software engineering skills, then it's the other thing. But otherwise, for data science, you won't be asked. Okay. But you can be asked like explain HM if you're applying for NLP role, like explain what happens in HM, right? So you need to explain the Markov chain, you need to explain the hidden state, you need to explain the types of probabilities, how the probabilities will get generated, right? But you can mention like there is a Viterbi algorithm, which is a dynamic programming algorithm, which will help us in efficient computation. But they won't expect you to know the working of Viterbi algorithm because you have not studied dynamic programming. Okay. So generally software engineers have one full round on dynamic programming. Okay. For like FANG level companies, they have a solid 1 hour round in which they are asked to solve code problems of dynamic programming. Like they're asked to build all the states by scratch. And that is the reason why they have mentioned it over here. Okay, I'll share this in the chat. You can go through this document. Okay. So this wraps up our HM. Okay. There are two things which are left for us. One is the chatbot, and one is deep learning. Okay. Deep learning again will be covering models which you already have seen. So I won't be explaining you like what is RNN and what is LSTM because those things you already know. Okay. We'll be focusing on.
MJ, you said in the first class you'll explain about transformers, but
Yes, that's a part of deep learning.
okay.
Yeah. So we won't be going into specifics of RNN, what is LSTM, because those things are common things which you have already seen, right? So we won't be covering CNN and all that, but we'll definitely see on how to use it. Same as we did for the previous lecture, where we didn't go into the specific of what is logistic regression, what is random forest, right? We simply applied it, right? Okay. In the final lecture, we'll discuss about chatbot. That's one thing. We'll talk about GenAI, LLMs. A little intro, we will have specific lectures on GenAI and LLMs, but a small connection of how GenAI is related with NLP and how chatbots are related to GenAI. And we'll talk about deep learning algorithms and we'll talk about the existing algorithm. Like we'll talk about the most complex one, which is BERT, which is the transformer. Okay. No, and we don't have to go into very specific of BERT because BERT is highly complex. No one is going to ask you the working of BERT, but over level they can ask you like explain in short what is the understanding of BERT. Okay? BERT, the transformers, the architecture of transformer, no one asks in nowadays. Okay? Because transformer is something which is very complex. Like it's impossible to explain or remember exactly every single thing. But we can remember the main concept. Okay? And that's what people will test you on. They will ask you whether what is the main concept used in transformer. Like, are you making an encoder? Are you making a decoder? How is encoder decoder getting connected? Right? Or if you only have to use an encoder, what will happen? What if we don't want to use a decoder? All this kind of questions you can expect. Cool. Any other question, guys?
Can you suggest any project ideas in this one, MJ?
Sure. So I would say once you have covered with the basic things, or let me actually share the screen. Right. The most difficult project idea is language translation, in my opinion. Okay. So if you can build language translation, it's an indication that you have something advanced in your project. Okay. But still, let me show you over here. Not only language translation, like there are other options as well, but language translation definitely is one complex problem. Okay, so here there are some simple ideas that you can see. Something which we have already covered. This is your sentiment analysis. Okay, so you have book recommendations, you have resume analysis. You can simply pick out the data set and start playing around with this. Okay, this is a language translation which is using the Hugging Face model. Hugging Face is based on Transformer. We are yet to discuss this. But again, here you're creating a model like ChatGPT. This is a very good project. I guess once we covered BERT, you will understand like how to create a chatbot, and through that you can create a question answering bot like ChatGPT. Okay, this again will be like a very good problem for you to practice. Okay, I think right now in NLP there are two projects which I really value. One is language translation, and one is question answering bots, which is chatbots. Okay, so probably if you have done the basics, then only go to it. Even if you don't go to it, even if you have sentiment analysis, if you have understood the core concepts, you should be able to get decent opportunities. Okay, it's not that just because you have complex projects, you will get it. A lot of times people will hire you based on the impact that you have created, even with the basic projects. So try to do the basic projects well and then go to the advanced projects. Okay. For any idea, you can like directly pick out from here. Okay. Best thing, just go over here, NLP, and search Kaggle and participate in a competition. Through that, you will have very good learning opportunities. Okay, go to competitions filter for NLP. Okay, NLP filter has already been applied, and you can see these are the competitions which are running. Whatever competition you feel is something where you have the skills, just participate in that. For example, you can do this classification task. Okay, because we have learned that classification, you know how to do this. Okay, so you need to build a model that recognizes toxicity. That is fine. Okay, so this is a little complex problem where you need to understand the evaluation metric, but still you can try this out. This will be a good project. A little complex, but you should be able to do it. If you get stuck, go to the code, see the other person's library and other person's notebook, just filter it by most votes and pick up this. Like this person has used LSTM, this person has used BERT. Uh, yeah, and you can check it out.
Can you share this link? This is work.
Yeah, sure. Right? You should be able to understand everyone's code majorly, okay? Because we have seen all of these things in detail, right? So I think this is based on toxicity, like it's identifying how much toxicity is there. But yeah, this is like pure exploration. It's just analyzing with different words, uh, how the toxicity is occurring with what combinations of words. Right? we have discussed multiple topics. Feel free to pick a topic of your interest. If you want to go with topic modeling, feel free to take a topic modeling. Like there are multiple things that we can pick up with. Yeah, so we can actually do this as well. Like you can find out the clusters based on the topics. EDA. I'm skipping the EDA. You can just check the counts of different bigrams, unigrams, and all that. This is fine. This is fine. This is fine. Removal, stop words, stemming, lemmatization. All this is done. Vectorizing, bag of words approach. They have only used bag of words. They are getting sparse matrix because they are using bag of words. They are doing topic modeling where they are using LDA. So NNMF is again another algorithm which you can read about, which is for topic modeling. Main thing we are focused is on LDA because that's the most famous one. NNF is again, I would say, second topic modeling algorithm which you can also read about. Okay, this is your found vectorizer. This is just fine. You have encoded everything. You're creating all the different states. Okay, this is the main topic modeling part where you're getting the different topics, right? As I said, it's like cluster. Topic 0, topic 1. It's identifying which sentences are similar. Okay, so every sentence you will have, for every sentence you'll have a particular topic. Okay, and based on how many number of topics you define. Okay, for example, here they would have said like probably keep 10 topics somewhere over here. Yeah, they said 11 topics. So here you will try to classify it into 11 topics. They have only said it till 10, maybe because they have already exhausted it. But there will be 11 topics which will be generated because the components that they have said is 11. Yeah. Did it start from 0? Oh yeah, it started from 0. That's why. Okay. That's it. You will be able to classify every sentence into a particular topic. Sharing this link as well. Start with basic projects. Don't directly jump into like advanced projects, else you will face issues while solving simple problems. If you learn basic things clearly, it won't take time for you to learn advanced things, right? Right now with deep learning, since you already have learned deep learning, it doesn't take time for you to pick up NLP ka deep learning, right? Because you already know the models. Only thing is you need to understand is how to apply those deep learning models. All right, it's 9:30. Let's wrap up. Any other question, guys? All right, then I'll see you tomorrow, and we'll end most probably in the final lecture where we'll discuss about chatbots and deep learning. Right. Thank you so much. Bye, and have a good day.